Every great achievement has required underlying vision and courage. Here in the control room of the Dresden Nuclear Power Station, you are witnessing such an achievement, as preliminary steps are taken to produce atomic electric power at the nation's largest all-nuclear power station. Dresden Nuclear Power Station is the first full-scale, privately financed atomic power plant ever built. Construction of this pioneer plant requires the actual invention, design, and development of nuclear equipment not even envisioned when the task was undertaken. Dresden Station is a significant contribution by the private utility and electrical manufacturing industries toward further advancing the prosperity of this nation, a nation where unparalleled living standards are built firmly upon electric power productivity. It is a giant stride toward making atomic electric power a practical means to provide for the enormous power needs of the future. Dresden is a symbol of vision and fortitude. In accepting the challenge of atomic power, Commonwealth Edison and her companion private industrial utilities of the Nuclear Power Group undertook the tremendous technical and financial challenges inherent in contracting for what was at the time merely a concept. The station also represents the mobilization of effort of the General Electric Company to bring to successful operation an integrated package of inventions, to manage its own capabilities and those of 1,500 other suppliers in the tasks of procurement, construction, testing, and training. This management task had to meet firm time and cost goals set 5 years before the operating plant would be turned over to Commonwealth Edison. To accomplish the difficult research and development objectives of Dresden, General Electric made major investments in new laboratories, manufacturing and test facilities, and in prototype equipment. Yes, in order to make Dresden a reality, many of the most important parts of the plant had yet to be invented. And General Electric scientists and engineers set out to develop the new concepts in boiling water reactor technology you see embodied in this model. The source of Dresden's power is the slightly enriched uranium dioxide fuel core within the pressure vessel. The moderator and coolant of the Dresden reactor is light water. Control rods inserted in the core control the fissioning process. The heat of fissioning boils the water within the pressure vessel. Dresden's reactor is known as a dual cycle reactor. Dual cycle because there are two sources of steam serving the turbine. In the primary steam system, the steam-water mixture produced in the pressure vessel is piped to the steam drum. There, the steam is separated from the boiling water and piped to the primary stage of the turbine at a pressure of 1,000 pounds per square inch and a temperature of 545 degrees Fahrenheit. The second cycle makes use of the hot water from the steam drum after the steam is separated. This hot water is fed to 4 secondary steam generators to produce additional steam at a pressure of 500 pounds and a temperature of 467 degrees Fahrenheit. This steam is fed to a lower pressure stage of the turbine. This is the way Dresden eventually would look, but much had to be accomplished first. Construction begins in November of 1956. Bechtel Corporation Engineer constructor for General Electric prepares the site. A few months later, excavation for the reactor containment sphere gets underway. This is the beginning of the more than 19,000 cubic yards of solid rock that must be excavated to provide a saucer for the huge containment sphere. Foundations are put in for the turbine building, which must be completed before bad weather sets in. While the excavation for the reactor containment sphere is being dug, concrete piping is installed to carry water to and from the turbine building. The concrete foundation for the containment sphere is begun. Massive steel support columns are the framework for the containment sphere. Meanwhile, the special steel plates for the sphere are being produced in the Greenville, Pennsylvania plant of the Chicago Bridge and Iron Company. The plates are shipped to the Dresden site. Here they are welded into sections. The first sub-assemblies are put in place around the midsection of the sphere to form the equator ring. As the containment sphere takes shape, the work necessary to make Dresden a reality continues at other locations. At its Vallecitos Atomic Laboratory in Pleasanton, California, General Electric has constructed the Vallecitos boiling water reactor to obtain vital development and design information for Dresden. Here, General Electric scientists and engineers simulate the complex technical problems of Dresden, study them under actual reactor operating conditions. A pioneer in its own right, the Vallecitos plant operates under Developmental Power Reactor License Number 1, the first to be issued by the United States Atomic Energy Commission. It is operated jointly with the Pacific Gas and Electric Company and furnished Northern California with the nation's first completely privately financed, commercially generated atomic electric power. Close by, work is underway on nuclear fuel development. Research is conducted on uranium oxide fuel that has been subjected to radiation exposures similar to conditions expected in the Dresden reactor. The radioactive fuel is investigated for such things as fission gas release, thermal and physical properties of fuel material, and isotope burnup. These and other complex investigations are necessary to prove the design of Dresden's fuel. In this critical experiment facility, a mock-up of the Dresden core is used to study core configuration and fuel loadings. At the nearby San Jose, California, General Electric manufacturing plant, 3 million uranium oxide fuel pellets are being produced for the 61-ton first core fuel loading of the Dresden reactor. Fabrication of fuel for Dresden begins in the powder processing line. The uranium oxide powder is mixed with a binder. milled until it is uniformly blended, and then fed to the presses where it is formed into dense pellets. After receiving a close visual inspection, the pellets are moved by conveyor to the furnaces, where the binder is removed, and the pellets are sintered to form very dense solids. After they have been carefully checked, ground to tolerance, and cleaned, the finished pellets are loaded into the zirconium tubes. The tubes are sealed, and the fuel rod segments are given a complete series of quality control tests. Only after all this thorough testing are the Dresden rod segments assembled into 11-foot-long fuel elements and readied for shipment to the Dresden site. In other areas at San Jose, different activities contribute knowledge for Dresden. Refueling procedures and equipment are studied in a full-scale test facility which simulates the conditions of manually refueling the Dresden reactor. Non-nuclear properties, such as steam rise rates and heat transfer of Dresden's fuel elements and reactor materials, are investigated in the heat transfer and fluid flow test facility. Design prototypes of the complex control rod drive mechanisms undergo rigorous testing. While across the nation, at the New York Shipbuilding Company in Camden, New Jersey, the pressure vessel that will house the Dresden core nears completion. Big as it is, the pressure vessel requires highly precise machining. The vessel is completed and thoroughly tested, then readied for shipment to Dresden. The 50-ton head closure is loaded first. Then comes the pressure vessel, 300 tons of it. After everything is aboard, the pressure vessel starts on its voyage to Dresden. Back at Dresden, the 190-foot-high, 3,500-ton containment sphere is completed. The sphere is a vapor-tight enclosure which houses the reactor and all the associated nuclear steam supply equipment. To make sure that the sphere welding is leak-tight, each weld on the entire sphere has been radiographed and tested under pressure with a soap solution, just as you might test an inner tube. It can withstand an internal pressure of 37 pounds per square inch to contain inside the sphere all radioactive vapors in the highly unlikely event of a nuclear incident. Completion of the sphere is the signal for the components to begin arriving at the site. The steam drum, pressure vessel, control rod drives, and other equipment arrive according to a predetermined schedule, and the task of installing the components for Dresden's steam supply system is about to begin. It takes 5 days to move the huge reactor vessel into the sphere. Other equipment moves into place. The secondary steam generator, the primary steam drum, and the high voltage power transformer. From this point on, much of the work takes place inside the containment sphere and the turbine building. Installing the pressure vessel, which has 5.5-inch thick steel walls and is over 12 feet across and 40 feet high, is quite a job. Once the pressure vessel is in place, the bottom core support plate is installed. Then the nuclear fuel arrives at the fuel storage building. The fuel elements are transferred to the fuel storage vault, ready for loading in the reactor core. At the reactor, the control rods and drives are installed. The control rods are mounted on the bottom of the reactor vessel to permit top access to the core. There are 80 control rods in the Dresden reactor. Each is positioned by individual rod drives operated from the control room. Miles of wire and cable are installed. Inside the sphere, the necessary components quickly come together. At the turbine building, the 180,000 kilowatt turbine generator, constructed and tested at General Electric's Schenectady, New York plant, is being installed. Later, auxiliary boilers will be used to ready the turbine generator equipment for nuclear steam. Slightly radioactive steam will pass directly from the reactor to the turbine, but maintenance of the turbine will be performed as in a conventional plant. When the turbine is thermally cool enough to be worked on, sufficient radioactive decay will have taken place to allow normal maintenance. Finally, all equipment is in place and ready for complete cleaning of the system and for the hundreds of tests that follow to prepare the plant for nuclear operations. Everything is now in readiness for the beginning of the sequence of events that will bring the Dresden reactor to criticality. All pre-operational testing of equipment such as control rod drives and instrumentation is complete. Every precaution has been taken to ensure that Dresden will operate according to calculations. The first step is taken as fuel is moved from storage to be placed in the reactor core. Fuel elements are transported through the fuel canal to the reactor pool. Loading continues with exacting care. General Electric physicists have computed that 28 fuel elements are required to achieve a critical mass, a sustained chain reaction. The 11-foot fuel elements are positioned in a carefully calculated array. And in the control room, everything is in readiness. At the control console, the operator unlocks the controls, selects the first control rod, and pulls it. One by one, additional control rods are withdrawn. The level of neutron activity is rising. The final rod needed to achieve criticality is withdrawn. And within 7 days of the target date set 3.5 years before, Dresden goes critical. A sustained chain reaction has been produced. The first stage in an exacting, prolonged procedure on the way to nuclear power production. Although 54 tests had been conducted before this first stage of fuel loading, great care is exercised during the period of critical nuclear testing to provide vital information for power operations. System adjustments, minor modifications, and most important, accumulation of vital data for design and startup of future nuclear plants must be accomplished. During this startup testing, the exact number of fuel elements needed for initial production of power is confirmed. Loading for power operations begins. and the dramatic moment nears when Dresden's first electricity will be produced. "448 elements are loaded, and the head is placed on the pressure vessel. More tests are carried out with the head in place, and the procedure for producing steam for the first time begins. More control rods are removed. More neutrons produced. The system is now heating. It's April 15th, 1960. As the system reaches rated temperature and pressure, and the operator rolls the turbine. An exciting moment as the plant's generator is synchronized with Commonwealth Edison's power system. Dresden is now on the line. The station is brought to half power as Dresden's first electricity is produced for the homes, farms, and industry of Chicago and northern Illinois. This is the culmination of 5 years of engineering effort. Dresden Station is a success. Following another series of exhaustive tests, Dresden was brought to full power of 180,000 kilowatts. On June 29, 1960, at full power, Dresden became the world's largest operating nuclear power station. Dresden in operation, proof of industry's drive for newer and better sources of energy. Completed ahead of schedule and within budget, Dresden is a dependable addition to Commonwealth Edison's system. Equally important, it is providing vital scientific information for even greater Dresdens tomorrow. Dresden Nuclear Power Station, courageous atomic venture, which in its success continues to contribute to America's progress.